All right, so we'll start. Good morning, everyone. This is the 7th lecture of Introduction to Artificial Intelligence, and today we'll be talking about something very important if you keep studying artificial intelligence, which is how to learn, how to make agents that would be capable of self-improvement. And the fields that we'll just introduce today are known as the fields of machine learning and the field of deep learning. So just to summarize where we are currently in this course. So today will be the 7th lecture on learning. This is the last lecture of this wet track, which was about probabilistic reasoning in general. So today we'll make use of some of the tools. So we'll still operate in this probabilistic framework to define the fundamental task of supervised learning. So we'll build upon mainly what we've seen in lecture 5 when we define probability distributions, and also in lecture 4 when we did a recap on probability theory. And then, starting from next week, we'll be merging everything that we've seen so far in this course. So next week we'll be talking about making decisions. So we'll try to merge the kind of adversarial search algorithms that you have been implementing in your second project with some kind of probabilistic reasoning. And so this will be the first lesson about this kind of tool. So we'll see Markov decision processes and then how to basically determine the best decisions within this framework. And then in lecture 9, the follow-up, we'll be mixing this Markov decision processes framework with learning. So this is what we'll see today. We'll see the ingredients today that we'll use in lecture 9. Then to implement agents that would be not only able to take rational decisions under partially observable environment and stochastic environment, but also under environments which are unknown from the start, and so that from which you would have to, with which you would have to interact and learn something from the observations that you collect. Okay, so we'll see how to implement this learning mechanism today, and so that in lecture 9 we have everything that we need to then talk about reinforcement learning, or at least to give an introduction to reinforcement learning. All right, so the topic of today is about learning, and more specifically it's about how to make our agents capable of self-improvement through some kind of learning mechanism. So through some kind of self-updating mechanism that would make the agents better by simply interacting and learning from their interactions with the environment. We'll see mainly two, so we'll divide this lesson into two parts. The first one will be about Bayesian learning. So we'll frame learning as a Bayesian update to our beliefs. And then second, we'll talk about supervised learning, or rather, I will give an introduction to machine learning using only supervised learning as a motivating problem, and then I will give you a quick intro to deep learning, which is a subset of the algorithm that you can use that you have in machine learning. If we have time, I will briefly mention a few things about unsupervised learning, but this is just bonus, and you should not consider that as part of the scope of this lesson or of this course. All right, so if we go back to what we started with in the very first lesson, when we try to define intelligence, and if we look now at what we have studied together, so we've seen, for example, search algorithms that you can that you can use to search a state space as specified by some domain knowledge, and you can then use these algorithms to make decisions. In your second project, you've also seen and used and implemented adversarial search algorithms that you can use, for example, for known and fully observable games. We've seen together also how to reason about uncertain knowledge, for example, as represented using probabilistic models that are motivated by some domain knowledge. Later on, we'll see how to take optimal decisions in lecture 8 and 9 under uncertainty and possibly under a partial observation. Also in lecture 2b, which is this optional lecture, I mentioned constraint satisfaction problem that you can use that basically exploit a known structure of the states, or also logical inference using well-specified facts and inference rules. And so all of these algorithms, all of these frameworks somehow can be used to implement some kind of intelligent behavior. Okay, and so they are sufficient to implement complex irrational behaviors, at least in those situations. But the question of today is really, aren't we missing a critical element in all of those? Okay, and the answer, of course, is yes, because as soon as you know these algorithms, they don't give you, at least in my opinion, a satisfactory answer at some kind of intelligence. They are just algorithms, recipes that you can follow, but it's not really intelligent by itself, right? And in all of these frameworks, what is common is that you have to start with something. Okay, there is some pre-specified knowledge that you have to give to the algorithm for them to work. So for example, in search algorithm, you have to specify what is the state space, what is the transition model. The same for the adversarial search. You have to define the transition models, the cost, and so on and so on. Or for the reasoning about uncertain knowledge, you have to start with a probabilistic model in the first place. The question is, how do we come up with these models that then we can use to in those algorithms, in those frameworks? Okay, and this is precisely what we'll try to answer today. We'll try to learn these things, this model, directly from the environment. Okay, and this is the purpose of learning. So basically, the question will be, what if the environment that we are dealing with is unknown? Okay, we are interacting with an environment, but we don't know too much about it. All right, so we don't know what will be the outcome of some action if we are in some state. We don't know what will be the resulting state, or we don't know the cost that we'll have to pay if we take some action starting from some state. And even less about the long-term reward that we'll eventually collect. And so then how can we use everything that we've seen today so far in this kind of unknown environments? And so the answer is to use learning, and to use learning as some kind of system construction method. Okay, and basically the idea that we'll use is to expose the agents to reality and to interact with reality or with this environment, rather than trying to hard-code reality or the environment into the agent's program. All right? And the algorithm that we'll see, or that we'll just introduce, will provide some kind of automated way to modify the agent's internal decision mechanism to improve its own performance. So if we go back to our diagram of learning environment, of learning agents, everything that we've seen so far was about how to implement the performance element. Okay, so search algorithms, adversarial search algorithms, how to take decisions under uncertainty, all these kind of things are just different implementations of the performance element. But of course, what we would like to be able to do is to learn, or at least to be able to improve this performance element. All right? And so this is what will be the purpose of the a new element that we add to the agent program, which is the learning element. And this learning element will be able to basically change, to make updates to the performance element in order for the agents then to be better, all right? In addition to the learning element, which we'll describe today, you can also have in this learning agents a critique, which will basically observe the world through the same sensors or through other sensors as the agent. And this critique will provide some feedback through to the learning elements, all right? And this feedback, for example, could be what is the outcome of some action if we start in some state. And then given this feedback, then you will be able to learn, for example, a new or a better transition model, let's say. And the third element is the problem generator, which will be an element that you can use to identify parts of your current knowledge for which you know you are uncertain or you are not very good at. And that will force in some way the agents to make experiment in this part of the knowledge. So for example, if the agent does not know, or if you determine that the agent does not know what would happen if if Pac-Man goes straight into a ghost, then you will force from time to time the agents to make these experiments in order then to collect the appropriate feedback that you need to represent the entirety of the world or of the environment. So of course the design of the learning element will be dictated by what type of performance element is used. How do you implement the performance element will have an effect on the learning element. And then which functional component of the performance element you want to learn. Okay, and also how do you actually represent that functional component, and finally what kind of feedback is available. So for example, if we take the case of minimax or alpha beta search, in this algorithm, as you know quite well now, you need an evaluation function or at least a heuristic function that give you a good enough approximation of the evaluation function. And that's something that's quite difficult to discover or to hard code, to program, to specify beforehand. And that's something, for example, that you would like to learn. Okay, so I'm quite sure now with the second project you've been experimenting in how making your heuristic function better and better in order to have better, stronger and stronger Pac-Man agents. But of course, this is not very satisfactory because you are just putting your own intelligence into the program, and then the program is just static and not learning and not improving by itself, right? So that's one of the elements that you could that you would typically want to be able to learn just by interacting with the environment. So this evaluation function then can be implemented or represented in many ways. And one way we'll see is, for example, to consider a simplistic model, which model the evaluation function as a linear, a weighted linear combinations of some features or some that you can extract, for example, from the state. And then this function will then produce as output the evaluation value or an estimate of the utility that you would get if you were to perform this action in this state. And then the feedback that you would collect in this case, for example, would be whether or not whether you lose or you win the game. So this is true for the evaluation function component in minimax search algorithms, but you could have the same in other instances of this learning element. So for example, if you were to implement a simple reflex agent, what you need to define is a percept action function So given an input, given an action, then define some output. Define some action that you have to perform given this percept. That's something you could, for example, also that you could implement with a neural network, which we'll talk about today. And the feedback would be whether this action was correct or not. Or whether the action that you produce, that you predict, is the correct action. For example, if you were to observe another agent interacting in the environment. Okay, and you just like to mimic, to reproduce, to imitate what this other agent is doing. All right, so this was for the motivation. Now let's talk about how to actually implement this learning component. So in the first part of today's lecture, I will first talk about Bayesian learning. And so in Bayesian learning, what we'll do is that we'll frame this learning as a Bayesian update that we apply on some probability distribution pH over some set of hypotheses. All right. So we'll say that H is an hypothesis variable, okay, which can take values H1, H2, and so on. And we'll start with a prior pH, okay? And this is the thing that we'll have to start with, but then we'll be able to update this prior using Bayesian updates. And then we'll collect data, observation data, by interacting with the environment or just by letting the environment doing nothing in the environment and just observing the data, some data that we can collect from this environment. Okay, and we'll call this data T. Then, given this data, what we'll be able to do is to reweight or to compute the posterior probability of each hypothesis. All right, so we'll compute P, the posterior probability of P of Hi, given the data that we've observed in the environment. Okay, and through the Bayes rule, this can be written as our prior beliefs about the hypothesis times the likelihood of the hypothesis, so which is the conditional density of the data under that hypothesis, over the model evidence, which is the probability of the data, the marginal probability of the data. All right. And now, given that we have this posterior probability about some hypothesis, we'll be able to use that to make predictions. Okay, and the way we'll use it is, so we'll frame basically predictions as just determining or computing some conditional probability distribution of some variable x that we'd like to, for which we'd like to be able to learn its distribution given the data that we've observed. All right, and so this can be written as so this is as the sum over all hypotheses. All right, and for each hypothesis, we just predict how likely is x given the data under that hypothesis model. All right, and then we'll reweight each one of these predictions by the posterior probability of the hypothesis that we've computed before. And this is right. And since we've been, we'll assume also that we can rewrite P of x given D and Hi simply as P of x given Hi. All right, and the effect of the data will only appear to reweight the hypothesis Hi. So maybe to make things a bit more concrete, let's consider this example where, so what we want to learn is a model about the world, all right? And so we'll define several hypotheses. What could be good models of the world? And we'll consider in this example 5 different hypotheses. And so we'll try to reason about candies, bags of candies, in which we may have cherry candies that you see in red and lime candies that you see in green. Okay, and what we want to reason is what is basically the fraction of each one of these 2 types of candies in the world. All right, so we could have either 100% cherry candies in the world, and that's the only type of candies we would have, or we would have 75% of cherry candies and then 25% of lime candies on average. Or the bags of candies would be composed on average of 50% of cherry candies and 50% of lime candies. Or fourth hypothesis, we would have 25% of cherry candies and 75% of lime candies. And then finally, the fifth hypothesis would be that there are only lime candies in this world, right? And so when I say we have a prior on hypothesis, that means we have basically, we define what are our hypotheses, what could be different models about the random variables that we want to, that we have in the world that we consider, and then we would assign a prior probability to each of them, all right? And so we would say that the first hypothesis has a prior probability of 0.1, then the second of 0.2, the third of 0.4, the fourth of 0.2, and the fifth of 0.1. And now, given that we start with this prior belief, the question will be, so what we'll try to do is to update this prior belief given some observation that we collect from the world, okay? So this observation, typically, in this case, would be that we observed some candies. And given these observations, what we want is to refine our prior knowledge. So let's say that we take some bag of candies, and the candies that we draw from these bags are 10 lime candies. Then the question is, how should we update our prior beliefs to better reflect or to take into account this observation? Of course, when you see that there are only 10, that there are 10, that when you observe that you've found 10 lime candies, then intuitively what that means is that you should increase your beliefs about this fifth hypothesis, and you should decrease the prior beliefs about the others, okay? But you should not necessarily make them to 0, because these are just average fractions of candies that you could observe, okay? And they are not saying that in every bag of candy you will have exactly 25, for example, for the fourth, that you will not have exactly 25% of cherry candies and 75% of lime candy. This is just the average proportion of the 2 types of candies you may have, okay? And so that means it's, for example, for the fourth hypothesis, okay, this can still be quite consistent, okay, because it may just be that you were unlucky and that you have never drawn any cherry candies because they had only, under this model, a probability of 25%. And then the question, and then in terms of prediction, what you could then, the kind of prediction you could make with this kind of model is, for example, what will be the flavor of the next candy that you will draw from the bag? And very likely the answer would be that, well, I think it will be a lime candy. And this is something that I can compute using the prediction as the likelihood weighted average over the hypothesis, where each of them is weighted by the prior belief, the posterior belief that you have about this hypothesis. So if you then do that and you evaluate the posterior probability of each hypothesis given the data, as you increase the number of samples in D. So D is basically a set of observations, right? And in this set, at least for this plot, what you have is that you only observe lime candies. Okay, so what you observe is that very quickly the fifth hypothesis gets stronger and stronger. Okay, which is what you would expect. The fourth hypothesis, at first it's consistent. At first it's also you put more weight. The weight of this hypothesis increases with the observation that you get, but as you increase the number of samples, eventually the probability of this hypothesis also vanishes to zero, and the same for all the others because they are even less consistent with the data. So this is consistent with our intuition. As you will get more data, you will, if in your prior you have the true hypothesis, then it's eventually that hypothesis which will stand out among all the others. And this is the hypothesis on which the density of the posterior will basically concentrate. Now that we have the posterior probability of our hypothesis, we can use that to make predictions, all right? And so that means we can compute, for example, the probability of the next candy being lime given the data D that we've observed as we increase the number of samples in this data. And what you see also, which is consistent with our intuition, is that as you increase the number of samples, that probability tends to 1, which is consistent with the truth if the lime candies were indeed drawn from this fifth hypothesis. Okay, so that example illustrates the fact that the Bayesian prediction eventually agrees with the true hypothesis, and on the other hand, that the posterior probability of any false hypothesis eventually vanishes as you get more and more data. So to come back to this, maybe this hypothesis space is something a bit vague, but to make it more concrete, so there is this example with the lime candies. If you were, for example, to consider the case of Pac-Man, the kind of component that you would like to learn is the transition model. Okay, if you assume that you don't have it, then you would like to learn it. So given some state, given some action, what do you predict for the next state if this is if this is stochastic? So you could start with a set of different hypotheses, different transition models that you assume, and then reweight each of them as you interact with the world. Okay. Unfortunately, summing, when you make predictions, summing over the entire hypothesis space is often intractable. So in the previous example, it was tractable because we were only considering 5 different hypotheses, but typically this space of hypotheses would be infinite. So there is no way, usually you will be able to compute the resulting integral analytically. So you could either approximate this numerically, but then this comes with some issues, or you could just simplify the problem, and instead of saying you want to aggregate over all possible hypotheses, you would just pick one of them among this set of hypotheses that you maintain. All right? And so the first choice that you could make is to say that you will pick and use the hypothesis for which the posterior probability is the highest, the largest. Okay, so that means you will want to determine the hypothesis H, which maximizes the posterior probability of H given the data that you've observed. All right. So this is the same as simply maximizing, so you can use the Bayes rule up to the model evidence, and so the posterior density can be written as the product of the likelihood times the prior. Okay, with the Bayes rule you should have also the model evidence which appears, but since you are maximizing with respect to H, the P of D term that you would have is not important and would result in the same solution, so you can just remove it. And then usually what we make also is that instead of directly computing the hypothesis H which maximizes this product, we take the logarithm of this product, and so rewrite this product as a sum of two logs. So the logarithm of the likelihood of the hypothesis plus the logarithm of the prior probability of the hypothesis, right? And so in this, all these three expressions are equivalent when it comes to finding the maximum a posteriori estimate. But if you look at the third one, you can view it as you will pick the hypothesis HI, which will maximize which will maximize the negative number of bits that you need to encode the data under that hypothesis, plus the number of bits that you need to encode the hypothesis itself, right? So remember that a probability value is something between 0 and 1. So the logarithm of that is a value between minus infinity and 0, right? So this is why it would be, in this case, maximizing the negative number of bits. And maximizing the negative number of bits is the same as minimizing the number of bits that you need to encode the data. Okay? So this is basically the same idea as picking the hypothesis, which would give you, which would correspond to the minimum description, which would correspond, to minimum description length learning, or to the Occam's result. Okay, so you want to pick the hypothesis under which the data that you've observed takes the least number of bits to describe. Okay, so and of course you have to encode to pass on, to provide the information that you need to describe the hypothesis itself, which is given by this prior. Okay, and so finding this maximum a posteriori hypothesis, the MAP hypothesis, is often much easier than Bayesian learning because it only requires solving an optimization problem, this optimization problem, rather than trying to solve or to compute some large integral over all the hypotheses. But this is an approximation of what you would like to do as a Bayesian. The second choice that you could make is to observe that as you get more and more data, then the prior beliefs that you have about hypothesis becomes actually irrelevant. Okay, you could just make it would be the same as if you were not starting with any prior. And so in this case, what you would simply have to maximize is, or the hypothesis I would like to identify is the maximum likelihood estimate, which consists in using the hypothesis for which the likelihood is the largest. Okay, so this is actually identical to the maximum a posteriori estimate when your prior is uniform, because then the prior would not depend on the hypothesis if it's uniform. So you would have this expression in which you can simplify the prior term, because it would not depend on age, and then that would result in this expression for the maximum likelihood estimator. Okay, and so maximum likelihood estimation is typically the standard statistical learning method that you will find in machine learning when it comes to non-Bayesian statistical learning. Okay, and so we'll see, this is, for example, the kind of principle that we'll use to define simple machine learning models, but it's also the principle that you will use, that we'll use together to then optimize neural networks. Okay, we'll basically try to identify the hypothesis, so some configurations of our models for which the density of the data is maximized. All right, so this is the optimization problem that we'll be dealing with today. Now, the recipe that you should use to actually solve this is actually often quite simple. So the first thing, of course, is to choose a parameterized family of models that describe the data. Okay, so that means you have to specify this P of D given some hypothesis. Okay, and so we just say that this probability distribution is some parametric model, some parametric probabilistic model, for example, a Bayesian network, or it could be a neural network, or it could be other things, but something which depends on parameters, okay, but otherwise is fixed, and that describes basically the likelihood of the data, or that describes the density of the data. Then, once we have defined this parametric family, the second step that we'll do is to write down the log likelihood L of the parameters theta. So theta will represent all the parameters that you need to specify one instance of this family of models. Okay, and once we have defined the log likelihood of the parameters, we'll write down the derivative of the log likelihood of the parameters, and finally we'll find the parameters theta star such that the derivatives are 0, and we also make sure that this then corresponds to a minimum or to a maximum because we want to maximize by making sure that the Hessian is then negative definite. So I've moved on now from a set of hypotheses, right, which I was calling HI, to a single model which depends on parameters theta, and then I want then to do optimization on these parameters theta. Okay, but you could just view these theta as some kind of instances or enumerations of the hypotheses that you consider. It's just that all these hypotheses are somehow tied together through the parametric distribution that you assume for P. So, as an example, let's consider how we could do parameter estimation, so how to find this theta in Bayesian networks. Okay, so we would say first, for example, that we want to determine that we have a Bayesian network, okay, where we have only one variable, which is the flavor of the candies that you observe. Okay, and so we would have this Bayesian network, and so this node corresponds to a random variable to which we attach a conditional probability distribution, okay, as we have done so far. But what will be different now is that this conditional probability distribution will not be static or will not be fixed. But what we'll do instead is that we'll parameterize this conditional probability distribution in terms of a parameter, in this case theta. So we'll say that the probability of the flavor corresponding to cherry is equal to theta. All right, and now given the observations that we'll collect, what we'll try to do is to determine what is the best value that I should use for theta. Okay, and so this is what we'll do, and when we say that we are learning about the parameters theta. The second, so of course you could also model things that are more complicated. So you could, for example, assume this two variables Bayesian network in which we have a flavor, which is also annotated with a conditional probability distribution for the flavor being equal to cherry. But then also we'll try to model what should be the color of the wrapper around each flavor. And so we say that this is itself defined as a conditional probability distribution where the probability of the probability of the wrapper being red, for example, given that the flavor is cherry, is equal to theta 1, and the probability of the flavor of the wrapper being red, given that the flavor is lime, is equal to theta 2. Okay, so in this model, then we'll have two different random variables that are tied together to this parametric model, this Bayesian network, and in which we'll have three different parameters, theta, theta 1, and theta 2, that we'd like to determine given the data that we have. Okay? So if we do maximum likelihood estimation, or if we follow maximum likelihood estimation, then we can actually determine quite easily these best parameter values for theta, right? So if we take this first Bayesian network and we follow this recipe, this is what we would get. So the question that we want to answer is, what is the fraction theta of cherry candies that you should use as best parameter value? Okay. So any value of theta between 0 and 1 is possible. So that means now we'll be dealing with a continuum of different hypotheses, okay, H, which will depend on theta. And theta will be a parameter for this binomial family of models. Okay. Now suppose that we unwrap n candies. So suppose that our dataset D is composed of n different candies. And out of these n candies, we obtain C cherries, and we obtain L being equal to the complement, so n minus C lime candies. Okay. If we assume that these observations are ID, so independently and identically distributed observations, therefore that means we can rewrite the likelihood P of D under some particular hypothesis H theta as the product of the individual conditional density of each observation under that model. All right. So if we say that this random variable is distributed according to a binomial distribution, right, then that means we would have a probability theta of observing a cherry, and a probability being equal to 1 minus theta of observing a lime candy. Okay, so that means this product can be rewritten as the product of theta to the power of C, the number of cherry candies that we've observed among the n candies that we've unwrapped, times 1 minus theta to the power of L, the number of lime candies that we've observed. Okay, so that corresponds to the likelihood. Okay, so we've just partly solved this second step to write down the log likelihood L of the parameters theta. If you take now the log likelihood, which I will call L, okay, you take the log of this product, so the log of this, which is equal to C times the logarithm of theta plus L times the logarithm of 1 minus theta. Okay, and this is the expression that we want to maximize, okay, because we want to find the parameters theta for which the data will have the highest density. So how do you basically maximize these kind of expressions? Well, you just derive or express the derivative of this likelihood, right? So the derivative of L with respect to theta, if you remember your calculus, so we would have C times the derivative of log theta, which is 1 over theta, so that gives us C over theta, plus L times the derivative of the log of 1 minus theta, so that's L over 1 minus theta, and then times the derivative of minus theta, which is minus 1. And so in total, we would have c over theta minus L over 1 minus theta. And then we say, since we want to maximize this thing, this is being equal to 0, and then we solve for theta. And so when we solve this equation for theta, what we would arrive at is theta being equal to c over n. Okay, so this is quite intuitive in the end. So and this is so if you unwrap n candies, and then among these n candies you observe c cherry candies, then the estimate that you would use for the probability of candies being of the cherry flavor is c over n. So the proportion of the cherry candies that you've observed so far among all the data that you had. Okay. But so while this is intuitive, what you should understand is that this can be viewed simply as the consequence of first deciding on some probabilistic model. So in this case, the fact that this is the probabilistic model that you assume, you say that the data follows a binomial distribution with some parameters theta. Okay, and then given this parameter model to follow the principle of maximum likelihood estimation to then derive the optimal values for theta. Okay, so this seems quite sensible, but of course you will have an issue when n is equal to 0. Okay, so when n is equal to 0, what should you do? So this is an issue if you just follow maximum likelihood estimation, but which will not be an issue any longer if you are completely Bayesian and then instead use the maximum a posteriori estimate, because in this case you would just follow, you would just reduce to your prior, okay, for which all the prior density would be properly defined, and so that means you would just pick the one which is the largest. All right, so we can do the same for the second model that we have described. So now if we want to model the world of these candies, where we would have two variables, one for the flavor, the second one for the wrapper, okay? We would say that we start with this Bayesian network, which is parameterized in terms of theta, theta 1 and theta 2, okay? And now, given the observations that we obtain, we would like to determine the best values. Okay, so we'll just do the same again. We'll express first the likelihood for each parameter configuration. Okay, and then we'll write down the log likelihood. We'll take the derivative of this log likelihood. We'll make it equal to 0, and then we'll solve for theta. Okay. So now what is different is that the color of the wrapping depends probabilistically on the flavor. Alright? So for example, the likelihood for a cherry candy in a green wrapper, okay, will depend of course on the parameters value that you set in the Bayesian network. Okay, but because we assume some structure for the Bayesian network, we know that we can rewrite this thing as the conditional density of the flavor cherry, given some parameterization, times the conditional density of a green wrapper given a cherry flavor. Okay, and so in this case, if we just then read off the density value from the Bayesian network, we know that this is simply expressed as theta times 1 minus theta 1. Okay, now we can do the same when we have not one but n candies, among which we have RC red wrapped cherries, GC green wrapped cherry candies, RL red wrapped lime candies, and GL green wrapped lime candies. Okay, so in this case the likelihood would expand as this product. Okay. Yes. So you have this first term which corresponds to the likelihood of for the flavors, and then you have the conditional likelihoods for the wrapping given the flavors. All right. Now the log likelihood of this would be equal to c times the logarithm of theta plus L times the logarithm of 1 minus theta plus RC times the logarithm of theta 1 plus GC times the logarithm of 1 minus theta 1 plus RL times the logarithm of theta 2 plus GL times the logarithm of 1 minus theta 2. Okay? So this is a bit long, but nothing difficult so far. Then we take the derivatives of this log likelihood with respect to each relevant parameter. So in this case, we would have 3 derivatives, one for theta, the other one for theta 1, and the third one for theta 2. We write them down. So the derivative of the log likelihood with respect to theta is the same as before. We make it equal to 0. The partial derivative of the log likelihood with respect to theta 1 would be equal to this expression. We'll make it equal to 0, and the same for theta 2. And now we are left with a system of 3 equations, okay, that we have to solve for the parameters. So these 3 equations there. And if we do that, then what we'll arrive to is the maximum likelihood estimate being such that theta should be equal to C over C plus L, which again is the same as before. C plus L is nothing else than N. So theta should be set to the proportion that you observe of cherry candies. Then theta 1 is equal to the number of red wrapped cherry candies among all cherry candies that we have seen. And so we would have so RC would correspond to the number of red wrapped cherry candies, and GC to the green wrapped cherry candies. Okay, and similarly for theta 2 for the lime candies. Okay, so again, this is in perfect agreement with what we would use intuitively to set all these values. But what I really want to stress is that, again, this is just a consequence. This is just a consequence of first assuming a parametric probabilistic model, and then following the principle of maximal likelihood estimation. So in the chat, I have the question: why do we not consider the Hessian? So in this case, it's not needed because all these functions are concave. So we know that the values that we'll achieve, the values of theta 1 or theta 2 that will coincide with 0 will correspond to a maximum. All right. All of this may seem maybe a bit abstract with respect to our initial motivation, but really we should see this, the maximum likelihood estimation principle and the maximum adversary principle, as really the core principle that you should follow, that we should follow, that we will follow when we want to do learning. Okay, and so we'll see how these things unroll when it comes to machine learning, which we'll now talk about. So it's 10, I think it's a good time to make a break, since that would correspond to a new part of this lecture. So I propose that we resume in 10 minutes from now. If you have questions about this first part, please write them down in the chat, and then I will answer them before we resume. But otherwise, we'll resume in more or less 10 minutes. All right, so we'll resume. So in the first part of today's lecture, what we've been talking about is what I could define as Bayesian learning, in which you start with a set of hypotheses, and then you use Bayesian updates to compute some posterior beliefs about this hypothesis. And then once you have this hypothesis, then you can use them to make predictions using, for example, all hypotheses together to make individual predictions, but which you aggregate through a weighted sum, and the weights are given by the posterior belief of each hypothesis. So this would work, but usually this is quite difficult to achieve because you would have to solve or approximate a very large integral. And instead what you can follow are the principles of either maximum a posteriori estimate, which is consistent with the Bayesian framework, in which you pick the hypothesis which is for which the posterior belief is the largest, or you follow the principle of maximum likelihood estimation, which is the hypothesis which maximizes the conditional density of the data, okay, the likelihood term. And the two of them coincide with each other when the prior that you start with is a uniform prior about the parameters of your model. Okay, so now we'll move on to machine learning, and you will see that we'll be using these two principles, mainly the maximum likelihood estimation principle. So don't forget about them. We'll be using them very quickly. So to start with, the question I would like to ask you is, let's say I give you a data set of pictures in which you have pictures of cats on one hand, and on the other hand you have pictures of dogs. Now the questions that I would like to ask you, given that you are third bachelor computer scientists or engineers, how would you write a computer program that would be able to take these images as input and then tell whether or not there is a cat or a dog in this image? Okay, so how would you write a generic program to be able to recognize cats and dogs in images? So I will just wait a few seconds because I would be quite curious to know how you would do that. So feel free to just write down your IDs in the chat. I know there is some delay, but that's fine. I think it's better to have a discussion about this. At least we'll try. If you don't have any ID, just tell me so in the chat as well. Okay, so two answers already. So you could try to detect shapes or forms. Okay, but so how would so you could, for example, detect, I suppose, triangles, circles, squares, but how would you compose these detectors in some way to tell that this is a cat or this is a dog? So another answer is to use the color changes among pixels and see how they are distributed. Okay. So indeed you could use the color changes as a way basically to detect edges. So for example, if you look at this cat, there is a gray background, and then there is a change of color for the fur, which is brown orange. And because you see the change of color, we know as humans that this corresponds to a hedge, and this corresponds to the body part, in this case of the cat. But so this is something you could do, but how would you go as far as actually implementing the program which use this information to tell this is a cat or this is a dog? Because the change of color could also arise in pictures of giraffes, in pictures of cows, or cars, objects, inanimated objects. So how would you use this information to tell that, no, this is really a cat or this is really a dog? Okay, so another interesting answer, which is average the pixels to have a more compact image, and then have some samples of known cats and dogs, and then pick the one closest to an existing one. Okay, so that's actually quite a good, would be a quite good approach, which is reminiscent to what is known as template matching, in which you have some kind of database, which I gave you, in this case of cats and dogs, and then you compute some maybe more compact representation of these images, for example, by averaging the pixels. And then when you are given a new image, then you, I suppose, compute also the same kind of average pixel representation, and then look for the closest among your database of images. And then you would predict the class, dogs or cats, associated to this closest image. So that would work at least to some extent for pictures of cats and pictures of dogs. But then if you build this system, and then I give you a picture of giraffe, given that in your database you only have cats and dogs, I don't think it would work quite well, because you would associate this giraffe with the closest image, which would be either a cat or a dog. And of course, that's not the right answer. All right, so let's move on. But yeah, the intuitive approach, or one of the simplest approach, if you were, for example, to write a program that would be able to identify cats or recognize cats in image, would be to say that, okay, I would be writing down my program such that it looks for body parts, because I know that a cat has a head, and then in this head there are usually two pointy hairs. There are two eyes in the middle of the face. There is the mouth, then there is the body, and to the body I know we have four legs that are attached to it, and there is a tail. All right. So I could say that, okay, I will try to look for all these parts, and then if they nicely connect to each other in the way which makes sense, so you could not have pointy ears attached to the tail, of course, they should be attached to the head, then I would say that I think there is a cat in this image. So this is the approach which has been used for several decades. I would say since the 60s to the end of the 2000s, and this is why I call it the good of old-fashioned approach. But even though it may work to some extent, it's also very brittle, in the sense that if you show in the sense that the system would really expect images in some way, while reality may be quite different. So for example, you would expect that cats are always seated, or they stand on their four legs, but reality is really not like this. In reality, you could have pictures of cats like this, and if you apply then your feature detector, your shape detector to this image, that would not work quite well. Even though as humans, it's still quite easy for us to say that there is a cat in this image. But if you were to look for these compositions of shapes, as we defined it, then it's much more difficult. Okay, so this system, this approach is very not robust. It's not very robust, and basically in machine learning, we would say that it does not generalize very well, meaning that if you expose the system to new images, then usually it will not perform quite well. It may work quite well within the realm of images that you started with, but as soon as you go outside of this, then the system just breaks. So the modern approach, which is the deep learning approach, consists instead in defining a very powerful parametric model, which we call a neural network, and to which we feed images. So what you see, the rectangles, are some abstract representation of a neural network, which you can view as some kind of slices or layers of sensors. So for example, in the first layer would receive as input the whole image, and then the sensors from these layers that we call activation functions would then trigger, so would just turn on or off if they see something specific in the input image, all right? And then this second layer then would produce as output another kind of image, and this other kind of image would then be fed as input to the next layer in the network, okay? And you would do that repeatedly for a certain number of layers until you arrive to a representation of the image. So you start from the pixel representation down to something very abstract, which boils down to volumes of numbers or a vector of numbers. And then given this vector of numbers, then you would build, use this representation for as input to a simple model like a linear classification model to then finally produce as output, this is a cat or this is a dog. Okay? And the idea is that this neural network will be quite powerful, meaning that it will be a parametric model with up to millions, dozens, or even hundreds of millions of parameters. Okay? And what we'll try to do is to adjust all the parameters of this model, of this system, such that when it is shown images from our training data that are from cats or dogs, then the configurations of the parameters make it such that the output is the correct output. Okay, so we'll keep adjusting the parameters, so the inside, all the knobs in this neural network, such that eventually we find a configuration which produce correct outputs. Okay, but so that assumes, of course, that we have a large training set. So that we start with a database of images, which contains also several hundreds of thousands of images of cats and dogs. But under this assumption, then we'll be able to train the system. And so this is the deep learning approach, and this is really what is giving the state-of-the-art performance in most of today's AI systems. So we are really no longer using this kind of shape detector approach. Instead, we would let the neural network learn what is the right, what are the patterns that I should look for, okay? And these patterns, so for example, so this is very abstract what I'm telling you about today, but you can really understand this as that. So the very first patterns that you would need to look for are, for example, triangles for the ears, circles for the eyes, another triangle for the nose, and so on and so on. And so all of these things would not be hard-coded in the program, but would be learned by the neural network. Okay, and they would be learned because the layers would be themselves would act themselves as some kind of feature detector, but a parametric feature detector, which depends on parameter that will learn. Okay, and then since this layer would produce as output another image or some kind of new image, then we would feed this new image to the second layer, and these compositions or succession of layers from one to the next is how we would actually define how we should compose these simple patterns together into more complex patterns. Okay, so for example, we know that the head is a combination of two pointy ears, two eyes, and a nose. Okay, and that's something, for example, you could determine as soon as you've detected individually the ears, the two eyes, and the nose. Okay, and so this is also what would happen, for example, in the next layers. You would look at the patterns that have been detected in the previous ones and then compose them together in order to activate for for more abstract or more generic patterns, like so compositions of these patterns, elementary patterns. So this is for the very abstract explanation, and now for the rest of this lecture, we'll see how we can actually implement these kind of models. So how they are actually defined mathematically, and how we can actually tune these parameters such that they reach good performance. So we'll start with the problem statement. So we'll assume that we have some data set D, okay, which is drawn from some joint probability distribution over observations X and some value Y that you would like to predict, okay? And we would say that we have n example of such input-output pairs, okay? So in the case of cats and dogs images, what we would have are images X of cats or dogs, okay, which are represented by the pixels of these images. So this would correspond to the X part, this X random variable, and the Y random variable would be the label that we want to predict, which in our case would be either cat or dogs, okay? And so the xi's are the input data and the yi are the outputs, and we would assume that the yi are generated by some unknown function f, such that yi is equal to the output of this function f when it is passed as input the x data. Okay. Now the goal of our problem will be to try to find a function h, so to find basically an hypothesis that will approximate this true function f. Okay, so basically we are given only y's and x's, and what we want to try to find is this unknown f function, which is mapping the two quantities with each other. Okay. So we could adopt this deterministic view, but in general, I think we should rather assume that this f function is stochastic in some sense. And so in this case, the y value, the y random variable, is not strictly a function of x only, a deterministic function of x only, but is probabilistically related to x. Okay. So what really we'll try to learn is or to approximate is the conditional probability density or the conditional probability distribution P of y given x. Okay, so given some input x, what I want to determine is the conditional distribution of the y variable. Okay, and so most of supervised learning and machine learning is actually about solving this problem. So how to determine this conditional probability distribution, and the way most of them work is by using the principle of maximum likelihood estimation on huge parametric models. So basically what we'll do is that we'll assume that P of y given x follows some parametric model, for example a big neural network, or a simpler model like a linear regression model. This model will depend on some parameters, and what we'll try to do is to adjust the parameters of this model such that the data that we have in our training data have a likelihood or are chosen such that these conditional probability values are maximized. Okay, so basically we just follow the maximum likelihood estimation principle to adjust the parameters of this parametric model. Okay, and so in what I'm talking about today, this problem statement is known as supervised learning because we are given explicitly pairs of x and y's. So it's like telling to the program, this is some x, this is some y, and I'm supervising you, and I want you to make correct predictions for this pair. Okay. But with other instances or other problems in machine learning, like unsupervised learning, semi-supervised learning, and many others, but these are out of the scope of this course. All right. So now that we have defined properly the problem that we want to solve, which is about approximating this P of y given x, the first thing that we have to do is to represent the input data. So to choose a representation for the x values. So usually what we'll assume is that the input samples x are described as real valued vectors with the different components. Okay, and these components, we call them attributes or features. Okay, so if some of you have already started maybe looking at machine learning, the components of these vectors, this is typically what we call features. Okay. On the other hand, it may be that the data that you are starting with is not represented in this way as real valued vectors. Okay. For example, if you want to classify text, if you want to make prediction for images or other kind of data, okay, this data does not come directly in the form of flat vectors. Okay. So if that's the case, then for this algorithm to work, you will have to transform them to prepare the data such that the data that you will feed to this model will be expressed in terms of real valued vectors. Okay. So, for example, in the case of images, if this is the kind of data that you want to make predictions for, then you could just say that you take the pixel representation. So you would transform this image as a flat vector which has as many components as you have pixels, and each value of these components corresponds to the intensity of the corresponding pixel. Okay, but this is a choice that you have to make, and you could make other choices. You could say also that maybe you have some kind of feature extractor already, which will give you access to more abstract features, like for example the number of loops. If you know already that you would be dealing with digits, for example with these images, you could say that you have a program that gives you access to the number of loops. So in this case there would be one, because you have this loop here. And then use that as in the representation of the data. So this is a choice that you have to make. If you are dealing with text, you could say that the vector representation of the data is a vector which is as large as the size of your vocabulary, which could be thousands of elements long. And then for each element which corresponds to a word, you have counted simply the number of occurrences of this word in the text. Okay, and so this is a very simple representation, but which works usually quite well for many problems. It's not at all the state-of-the-art representation, but to start with and to make things simple, this is usually a good enough baseline. All right, so we'll start easy. So now that we've defined the problem that we want to solve, we've defined how the data is represented. What we'll do now is to try to actually solve this problem. Okay, so we'll first assume that the data that we want to predict, to make predictions for, so the y values, are real values. Okay, so this value can be any values on the real line. Okay, and the very first model that we'll consider is, so let's say that this axis corresponds to our features, to our x inputs, and this other axis corresponds to the y values, okay, the things that we want to make predictions for. Okay, in our data sets, we would be given pairs of x and y's, okay, and for example, they could be represented by these red dots. Now, given these red dots, a very simple that you could consider is to consider a straight line, so to basically linear combinations of the input elements, which when you combine them together should produce a value, a y value, a predicted y value, which is as close as possible to the ground truth value that you have in your training data. Okay, so if you do that, then basically what you want to determine is what would be the best straight line that would pass through this data that I have in red. And so a straight line is in this case simply defined by two parameters. So the initial offsets with respect to the origin and then the slope of the line. Okay, that's the two parameters that we would have to adjust in order to pass through this data. Okay, so in this case that's a very simple model, only two parameters, but we'll start with this. In terms of probabilistic model, what we'll say is that the linear regression model, so what we'll say is that we will assume that P of y given x. So again, what we have to define is what is the probabilistic model. So what is the form that I want for P of y given x. Okay. So what I will say is that this, and this is an assumption that you have to make. Okay. I will say that the y values are represented as a linear Gaussian model of the input values. So that means that I will say that the y value is Gaussian distributed, where the mean of this Gaussian is given by some linear combination of x, my input, and with some constant variance. Okay? And so the parameters of this model are the w vector and the b scalar value. So if x is only one-dimensional, we would go back, we would reduce to the two parameters that I was talking about, b, which is correspond to the offset, and a single w, which correspond to the slope. Okay, and these are the parameters that I want to determine. Okay, so basically what I will say is that given some x, for example there, I will say that the y values, okay, on average they are at a position w t times x plus b, okay, which is represented by this line, but they can be distributed around this line, okay, with some variance which I fixed to, for example, sigma squared. Okay, we could say it's unit variance. So this is why I'm allowing the line to not pass through exactly every dot, because in any way, since the dots are not perfectly aligned, this would not be possible to go through them with a single line. Okay. Now the question is, how do I find the w and the b parameter values? Well, we are just left again with an instance of a problem where we have some parametric model, okay, about in this case some relationship between y and x. We are given some data, okay, so we have two choices. The two choices that we've seen today is to do either maximum a posteriori estimation or to do maximum likelihood estimation. So we'll do maximum likelihood estimation. So to learn the conditional distribution P of y given x, we'll maximize the likelihood of with respect to our training data. Okay. So since we assume that P of y given x is normally distributed, okay, that means we are saying that the density P of y given x is equal to this expression, okay, which is the expression of the normal density. Except that we have replaced the mean parameter by wt, so w transpose times x plus b, and we have fixed the variance to a sigma squared. Okay. Now, how do we maximize this? Well, we will follow our recipe. So we'll write down the log likelihood of the parameters w and b, and then we'll make this likelihood equal to 0, right? And then we'll solve for W and B. And if you do that, if you do the derivation yourself, what you will find is that you will arrive to the problem which consists in minimizing the sum of the squared errors for the predictions, the mean predictions, Wt times xj plus b. Okay, so therefore that means minimizing the sum of squared errors actually corresponds to the maximum likelihood estimation solution for a linear fit, assuming Gaussian noise of fixed variance. Okay, so this is something I suppose you have seen before, how to fit a line given some points. Okay, and maybe you have seen that you should minimize this sum of squared errors. So this is the an instance of the least squares problem. Okay, this is quite standard, but what I want you to understand in this course is that this also can be viewed simply as a consequence of first assuming a probabilistic model. In this case, the fact that you assume that P of y given x follows a linear Gaussian model of this form, and then just applying maximum likelihood estimation given the data that you have. If you do that and then just unroll the computations, you would arrive to this objective. Okay, so this is just to show you that this loss, this function that you have to minimize, this objective, comes from somewhere. Okay. And so, of course, this expression has maybe a more intuitive explanation, which is given by this plot. So if this axis corresponds to the features for the data, and so f1x would correspond to the first feature of the data, what we would have is that, okay, the Wt times x, or f1x plus b, would give us the line in black. Okay, and the red point would still correspond to our training data. And now this difference there would correspond to this blue segment that we see, that we call the error or the rigid residuals, which correspond to the error that you make with the average prediction y hat. Okay, and what you want to do is to minimize this sum of errors. Okay, which is exactly what this is saying as well. Okay, so this model is quite important. It's very simple, but it's good that you understand how it is derived and what it does represent. This is something which we'll reuse later on when we talk about reinforcement learning. So we'll make use of this model to approximate some functions which are part of some of reinforcement learning algorithms. This is also something you will see with Antoine during the exercise sessions. And in any case, this is a tool that you should know about because the applications of this, of course, go beyond, much beyond artificial intelligence as a field. It's used in statistics and in many other domains, because it's so simple and a reasonable thing to do. But so it's maybe too simple because it assumes that there is a linear relation between x and y, which may not always be the case. Okay, and usually will not be the case. It also assumes some kind of distribution for y given x. We say it's Gaussian distributed with strict variance, but again, this is an assumption that we are making, and reality may be quite different. All right, so now let's move on to regression, to classification. So the problem that we've seen here, to fit a line when y is equal to can take real values, it's known as a regression problem in machine learning. When the quantity that you want to predict can take any value on the real line, this is called a regression problem. On the other hand, when the values that you want to predict are values taken in a fixed set, a discrete and symbolic set of values, for example, 0, 1, or cats and dogs, then the kind of supervised learning problem we will be talking about are classification problems. Okay, so in this picture, for example, you see that you have some kind of agent that want to take as input some text, some envelopes, or some emails, and then want to tell whether or not this email corresponds to spam or not. Okay, and if it corresponds to spam, then you should not show it in the inbox of the user. Okay. So the first model that we'll see to solve this problem is known as the linear. So the linear classifier model can be viewed as, or in this case would be defined as a squashed linear function of its input. Okay. So what we want to predict is either 0 or 1, for example, if you are dealing with two classes. And the way we would define our first simple model, or linear classifier model, would be to say that, okay, I will compute some linear combinations of my input with respect to some parameters that we would have to learn, W and B. And then if I look at the sign of this value, if the sign is positive, then I would predict 1. I want to predict the value 1 for Y. And on the other hand, if the sign is negative, then I would predict 0. Okay, so this is the hypothesis, the set of hypotheses that I will consider, and they would be parameterized by the W and B parameters that you see there in the expression on the right hand side. So without loss of generality, that model can be rewritten without this B offset. And the way you could do that is to add an extra feature, an extra component, which is constant and, for example, always equal to 1. And you would add this component to representation of X. Okay, so that means we could rewrite our hypothesis, so our prediction model for X, given some parameters W, as simply the sign of the linear, some dot product in this case, of W and X. Okay, and that would be strictly equivalent if we extend our representation with this dummy element, which we fix to a constant value. Okay. Now, this model, this simple model, has a nice geometric interpretation. Because if you have some data, for example, so if you say that your data X, for example, lives in the 2D plane, so you would have two components in X, and the values Y that you want to predict are either red or blue, so you have two classes, red or blue, 0, 1, then the way you would make predictions with this model is by computing the dot product between Y and X, okay, and then looking at the sign of this value. Okay, so that means if X and Y are two vectors that are aligned and they point to the same direction, then the dot product will be positive and will be a positive value. On the other hand, if they are aligned but in opposite direction, then you would predict so this quantity would be negative, so the sign would be 0, and that would be also a correct prediction. And on the other hand, if the W and X vectors are orthogonal to each other, then the dot product would tend to 0. Okay, and that means in this case the model would not know exactly what to do with this input X, because it would mean that the prediction would lie close to the boundary decisions that you see with the dashed blue line. Okay, so this dashed blue line, okay, is what is known as the boundary decision, which is the plane, the hyperplane orthogonal to the for which the W vector is normal to it, and everything which is above, or in this case on the left, would be classified, would be predicted as red, and everything which is below would be predicted as as blue. Okay. So now the question, given this simple linear classifier model, how do we find the W and the B parameters? So we could maybe think for a while and say, okay, this is again just a probabilistic model in some way. So I will use the maximum likelihood estimation principle that we have seen so far. So I would write down the log likelihood and then take the derivative of that log likelihood with respect to the parameters W and B, and then make it equal to 0 and solve. Unfortunately, that would not work because the derivative, because the function that you take the derivative of is constant, is piecewise constant. So that means the derivative would be 0 everywhere. And then it would be quite difficult to optimize. So first you would not have an analytical solution for W and B, and it would be difficult to navigate the space, the parameter space for W and B, because you would, the derivative would not give you any information about that, because it would be equal to 0 everywhere. Fortunately, there is a way to still learn the parameters of this model, and this is known as the perceptron learning rule, okay, which is one of the very first instances of neural network, which was invented back in the 60s. And so it goes as follows. First, we'll start with a W vector, which is set to 0. Okay, so all the elements of the vectors are set to 0. And then we'll have our training data, and then we'll loop over each training example, so over each pair X and Y. And then for each of them, what we'll do is that we'll classify, so we'll make a prediction Y hat for X given the current parameter values W. Okay, and so we'll look at the sign of this dot product. So the sign would be either positive or negative, so that means the prediction would be either 1 or 0. If the prediction is correct, okay, so if our prediction Y hat is equal to the ground truth value Y that we know from our training data, then that means we should not update the W vector, because this is giving us a correct prediction. On the other hand, if the prediction is wrong, okay, so if we have predicted 1, whereas we should have predicted 0 or vice versa, then that means the W vector is imperfect because it's giving us a wrong prediction. So that means maybe you should make an update to fix this error. Okay. So this is precisely then what you can achieve with this update rule. Okay, where you would say that so for example, if Y is equal to 1, okay, and then you made a wrong prediction, then you should simply move the W vector by adding X to W. Okay, or you can also have a learning rate in front of this term, but let's just keep things easy. So that means if if this blue line is our correspond to our current decision boundary, given this W vector, okay, that means for this blue dot, so this dot which is actually blue, we are making a wrong prediction because it's above this decision boundary. So we are actually predicting red for this blue dot. So we should update the parameter values for it. And so wait. And so now if Y is equal to 1, why is it in this direction again? So you should update in the opposite direction because you are making a wrong prediction. But why is it? Let me think again. So that would be 0 minus, okay. So this, yeah, sorry, maybe this figure is a bit misleading, but so this yi would correspond to this whole expression, okay, which then correspond to the opposite direction of x. So then we would update w, so we would update w into w plus yx minus 1 minus y times x. So either one of these two is actually different from 0, because either y is equal to 1 and we are predicting 0, okay? So in this case, this term is equal to x, and at the same time, since y would be equal to 1, 1 minus 1 would be equal to 0, so this would cancel. Or we would have the opposite thing, when y is equal to 0, but we are predicting 1, so in this case, this term would be equal to 0, and y would be equal to 0, so 1 minus 0, 1. Then we would subtract minus x from w. Okay. Okay, and so after the update, now the resulting w vectors would be equal to this black arrow, where you see that we have shifted now the decision boundary by a bit. It's tilted by a bit, so that now after the correction, the blue dot would be correctly classified, so we would make a correct prediction for this blue dot. Okay, and then you would keep iterating over the training data until you don't see any changes anymore to the w vector. Okay. So another way to see this, to understand this diagram or this update rule, is to look at this at this cartoon, where you would have blue dots and red dots, positive and negatives. If you are making a correct prediction, so if the blue is correctly is on the correct side of the decision boundary, you should not change anything. On the other hand, if you have an element which is on the wrong side of the decision boundary, then you should update the decision boundary such that now the red sample would be closer to the decision boundary, or even would then arrive to the correct side of the decision boundary. So this algorithm can be extended to more than 2 classes. So in what we have seen with this perceptron update rule, it's valid when y takes either the value 1 or 0, but you could say that you have more than 2 classes, more than 2 symbolic values to predict. Okay, you could have a certain number n of them. For example, you could have 3 of them, where you would have blues, reds, and greens. Okay, and so in this case, you could generalize the perceptron model by having a weight vector WC for each class C in your problem. So for example, if you have 3 classes, you would have 3 different W vectors. And then you would compute the activation for each class C as the dot product of the corresponding weight vector with the input data. And the algorithm, the update rule would be quite similar. You would start initially with all the weight vectors set to 0. And then for each running example xy from your training data, you would classify with the current weights. And now the classification would be a bit different. You would compute the activation for each class. Okay, so you compute the dot product WC times X for all classes C. And then you would pick as prediction the class for which this dot product is the largest. Again, if the prediction is correct, you don't do anything. Otherwise, you update the parameters, and you would do two things now. You would raise the score for the right answer, so you would update the W vector for the correct class by adding X to this W vector, and for the incorrect classes, so the one that you are predicting wrongly, then you would lower the score by subtracting the X vector from W. Okay, so this is something you can see, for example, on this video, where what you see are an example where you have three classes, red, blue, and green. The yellow arrows correspond to the current training data, training pair that you are considering. And what you want is to adjust the parameters, so basically adjust the three arrows such that your training data is correctly classified. And currently you see that this is really not the case. You are predicting red for all these green dots, you are predicting green for all these red dots, and you are making a few correct predictions for these blue dots. Okay? And so what we'll just do is to apply this multi-class perceptron algorithm on this problem. Okay, and so we'll keep iterating over the training data. So for example, here we see that we are making an incorrect prediction for this blue dot, for this red dot. So that means, and we are predicting this as red, we are predicting this dot as green. Okay, so that means we should update this arrow and the green arrow and the red arrow. Okay, so we'll subtract basically X from the green arrow, and then we'll add X to the red arrow, and then we just keep iterating over and over on the training data from our dataset. Okay, so you will see this going through. Up, so we've updated the two vectors, the one for which so the green and the red, and then we go to the next data point. Again, we are making an incorrect prediction, so we should fix the red arrow and the green arrow, and so on as we iterate over our training data. So if you continue iterating, you see already that more and more the points from our training datasets are correctly classified, meaning that we are making correct predictions for more and more of them. So now the red region has moved where there are red points, the green regions has moved where there are green points, and the blue regions was already quite good, but now it's even better. We are still making a few incorrect predictions. Actually, now it's perfect. We are no longer making any incorrect predictions. So all the dots, all the samples now are correctly classified. And so if we keep iterating, we'll see that we are not making any updates any longer, so we can terminate the algorithm. Of course, this would only happen if the training points are perfectly separable, meaning that you can indeed find there is a solution for which all the predictions would be correct. This is not always the case. For example, when you would have red points and blue points that would be overlapping, then there is no way you would be able to find a linear cut that perfectly classify all of them. And so you would have then to define another terminating criterion, but you understand more or less the idea, I suppose. Okay, so there is one question in the chat. If the method we choose to express the data as real valued vector is not really good, could we have blue dots on the red side at the end? Sure, yes. So how you project the data in this plane, in this Euclidean space, of course is important. And this is if the projection, the representation that you pick, you will project data points of different classes of different colors onto the same region, then of course you will not be able to find a linear classifier, so a plane that will separate them from each other. That's correct. And without spoiling you the story, what will happen with a neural network is that you will learn basically how to project the data such that in this projected representation, in this Euclidean, the resulting Euclidean space, it becomes easy to separate points from of different classes. All right. So this is a very simple algorithm. It's just a linear model, or maybe a few of them when you have several classes. But already this is quite powerful. So this is an example that I want to show you. So for example, can we learn to play Pac-Man only from observations? Okay. So to recap, what I will show you is that you can use this multi-class linear classifier to play the game of Pac-Man. Okay. So the way we would have to do that is first to define what is the input representation of my data. Okay. Or first, what is the model that I want to, what is the problem that I want to solve? Okay. So in supervised learning, what you want to determine is some conditional probability distribution between y and x. So what are the y's and what are the x's? So in our case, to play Pac-Man, the x's would correspond to the states and the y's would correspond to the action that you should take in this state x. Okay. And ideally, you would want to pick to predict y values, so actions, such that your agents play ways. Okay. What we could assume is that, for example, we are observing a very good agent, an expert, a grandmaster, playing the game of Pac-Man, and we would like just to imitate its behavior. Okay. So what we could do is to observe this grandmaster playing and then collect pairs of states, the x value, the input, and y's, the actions that the grandmaster is taking in the corresponding state. Okay. And so what we want then to find is what is the function, what is the mapping between the state and the actions that the grandmaster is taking in these states. Okay. So our input data, S, the states, we'll have to transform them into vectors. Okay. So we'll just say that we have some function g that takes S as input and then produce a vector representation x of the states. Okay, it could be, for example, I don't know, a vector which is as large as the number of positions in this map. Okay, and which would take, for example, Boolean values if there is a dot. We could have the same kind of, we could add also the same information for the capsules and for the ghosts. Okay, and whether or not you ate a capsule recently. Okay. And the y's would correspond to the actions. So in this case, what we would like to perform is a classification problem. Shall we go up, down, left, or right? Okay, and it's not we don't want to predict a real value. Just one of these four possible actions. These x and y pairs, state action pairs, would be collected by just observing this grandmaster playing, as I said. And then what we would like to learn is the actions that the expert would take in a given situation, meaning we would like to learn some mapping f from the vector representation of a state, x, down to the action space A. Okay, and this is a multi-class classification problem. Okay, so let's see what would happen. So first, let's say that you worked very hard and then you implemented a very good minimax agent, which is able to kill the ghosts by eating the capsules when there are multiple ghosts in the environment in order to maximize the score. Okay, so you would play once, and then you would collect all the sequence of state action pairs that have emerged from the Minimax agent. Okay, you could repeat that with a second episode of the game. Again, you would execute your very strong Minimax algorithm. It would play the game and then eat all the capsules in order to maximize the score, okay? Without being killed by the ghost, or maybe by killing the ghost if it eats some capsules. Now, we've collected this data set of state action pairs, and what we can do is to use this multi-class perceptron algorithm then to fit the weights of, so to fit all these weight vectors such that it would make good predictions given a state. So that given a state, it would correctly predict the action Y that the Grandmaster would have taken in this state. Okay. And now, after two training episodes, if we let the perceptron agent plays, okay, this is what would happen. All right, so what you see is that we arrive to a very strong agent, which is basically as good, or almost as good maybe, as the teacher, the Grandmaster. It properly solves the game without being killed. It even killed some of the ghosts, and at the end reached a score which is quite large. But what is quite different from before is that this agent is now just a very simple reflex agent, where you are given a state, then you process this state through the perceptron model, this multi-class linear model, to directly produce, to spit out the action that you should perform. And when you do that, that does not involve any explicit reasoning about what would be the consequences of the actions in the game, as you would do explicitly, for example, in a Minimax agent. Okay, and there is no more heuristic which is involved. Everything basically has been learned by imitating the Grandmaster. And again, you see that this implements some behavior which is far from being trivial. Okay, it's a policy that would be quite difficult to implement explicitly yourself in a program. Okay, and we do that with a very generic model, which is as simple as taking the sign, as looking at the sign of a dot product. Of course, the crux of the problem is to define a good representation and then to find a good weight vectors, but this is taken care of by machine learning algorithms, like this perceptron update rule. All right, so I see that it's already 11:15. So I will just make a last short break of, let's say, 5 minutes, and then we'll resume at 11:20 to talk about deep learning. Again, if you have questions, please shoot them in the chat, and I will be happy to answer them. All right, so let's come back for the third part of today's lecture. So now we'll move on. So we've briefly talked about machine learning, and what we did was to introduce the problem of supervised learning, in which you have two main problems. The first one is known as regression. What you want to do is to determine a mapping, a probabilistic mapping between some input vector x and some output y, which can take any value on the real line, let's say. And the second fundamental problem of supervised learning is classification. So either binary classification, when you want to predict either true or false, 1 or 0, red or blue, or multi-class classification, when more generally what you want to predict is a value among a discrete set of symbolic values. Okay, and we have seen basically a simple model to do that and to solve these two problems, which is to assume a linear model. So in the case of regression, this linear model directly predicts the y value, and in the case of classification, this linear model predicts some real value first, and then we look at the sign of this real value, and that gives us the prediction for the x input. Now, of course, these models, I've shown you that you can already solve some tasks, like playing Pac-Man just by using a linear model, and this seems to work quite well. But if we go back to our problem of trying to identify cats and dogs from in images, then it will be much more difficult to achieve that with a simpler linear model. Okay? So this is precisely now that what we'll see is how to make this model more and more complicated, and maybe to combine them in some hierarchical fashion in order to achieve even better performance. Okay? And so this is what we'll see in this third part about deep learning, which again is just a very short introduction about how that works. If you then become interested by these techniques, you should know that I'm giving a full course in the master program dedicated to deep learning across 10 different lectures, just dedicated to this family of methods. So today is just a very short introduction in 15 or 20 slides and no more than that. Okay, so the first thing that we can do is to start from a linear classifier, but to replace the set we use to squash the linear activation, to make it either equal to 0 to okay, I had some connection issue. I think it's back now. But so what I was saying is that you should, the first thing that we do is to replace the sign function such that the conditional probability of py given x will change smoothly with x. Well, this is not the case when you consider the sign function, because it changed. So if you look at this, yes. So if this is x, py given x either takes the value is either equal to 0 or 1, and as you move along the x-axis, there is no smooth change of value. Okay, at some point when you cross 0, there will be a change of value, but this is not a change which varies smoothly. Okay, so the first thing that we'll do is to replace the sign function by another function such that this will happen, and the result will be what is known as a logistic regression model. So the logistic regression model, contrary to its name, is a model to do classification, not to do regression. But it's a model in which we'll say that the conditional probability of the positive class y equal to 1 given x is given as a parametric model defined as the sigmoid activation of the dot product between y and x. Okay. And the sigmoid activation, which I denote by sigma, is a function which takes as input a scalar value and then produces as output another scalar value, which is equal to 1 over 1 plus the exponential of minus its argument x. And so if you plot this function with respect to x, what you will have is this kind of plot, which is actually more or less the same as the sine function that we had, except that now it's like a softened version of it, in which we don't have anymore this arc change from 0 to 1, but as we get closer to 0, then the value of the function of p, the value of the function of the model of the output will vary smoothly from one value, 0, to the other one. Okay? So this is a very simple model again, and maybe you may not understand why it would be better, more fundamentally better than the linear model that we've seen, and you would be correct. However, what we'll do is that we'll use this logistic regression model as a building block of neural networks. And what we'll do is that we'll compose this regression model together. So we'll consider several of them jointly. We'll compose them, and what we'll arrive to are a very powerful model that will be able to model, for example, non-linearities between x and y. And these resulting models are nothing else than neural networks. Okay, so let's first consider this very simple logistic regression model. This is the parametric expression that we'll consider. Again, we'll be starting with data, and again, what we want to do is to find a good parameters value of W and B. So before, what we did was to use this perceptron update rule, okay? And for reasons that I've not explained, I've shown you that indeed that works, and it manages to find a solution if one can be found. Now, the situation is a bit different because we are now dealing with a likelihood function which varies smoothly with its argument. Okay, so we could just go back to a recipe of following the maximum likelihood estimation principle. Okay, and this is what we'll do. So we'll have some data D, which is our training data. We'll assume a probabilistic model for the data, so for y given x. So this is the model that we assume. This is an assumption that we make. And then we'll try to maximize the likelihood for PD of the parameters W and B. Okay. So this, if we assume ID data, then we can rewrite this joint density as the product of the individual densities. Okay. So this expands into a product over the individual training pairs xi, yi that we have in our training data. And for each of them, we express the probability of the class of the yi value given xi and given the parameterization wb. Now, by construction, what we are saying is that this py, this conditional probability, follows this logistic regression model, which is defined in terms of this sigmoidal activations of the dot product between w and x. Okay, so if y is positive, so if yi is equal to 1, then that means that this expression reduces to the sigmoid activation of w times xi. And on the other hand, if yi is negative, so if it's equal to 0, then the probability of py of the negative class given xi is 1 minus the probability of the positive class given xi. Okay, it's the complement. Okay, so this is why in this case we would say that we would have either yi is equal to 1. Okay, in this case, the conditional probability of the positive class is equal to that. And at the same time, if yi is equal to 1, then that means that 1 minus yi is equal to 0, so this term does not appear. But if yi is equal to 0, what we want to say is that the priority of the negative class is equal to 1 minus the priority of the positive class, okay, which is expressed as 1 minus the sigmoidal activation of the dot product of w and xi, okay, and this term should be the one that we use when yi is equal to 0, okay, so this is why we use this trick of exponentiating these factors by the class yi or 1 minus yi, because this will activate either one or the other factor in the expression. So when yi is equal to 1, we have this expression and this other one reduced to 1, and vice versa. When yi is equal to 0, then this thing reduces to 1, while the other is equal to this expression. Okay, now if we take the, so we can express this product as a sum if we take the logarithm of it. And if we take minus the logarithm of it, what we arrive to is a minimization problem over the model parameters w and b of the sum over the training data xi yi of minus yi times the logarithm of the prediction minus 1 minus yi of the logarithm of the opposite prediction for the other class. And so this is basically the function that we'll try to minimize. This is our objective function, and we'll try to minimize it with respect to w and b. Okay. Unfortunately, now we no longer have a direct solution for it. We don't have an analytical solution for it, and so that means we'll have to resort to numerical approximation, numerical optimization algorithm to find good enough values for w and b. Also, just for your information, this function, this objective function, can be seen as an instance of the cross entropy, which we define as the expectation of minus the logarithm of some distribution q in expectation over another distribution p. And in our case, we would have p, which would be equal to the conditional, the truth value given xi, and q would be equal to the prediction variable y hat given xi. And what we want is for these two conditional distributions to coincide. Okay, and that would happen when the cross entropy is minimum. So we want the prediction, the distribution of our predictions to match with the predictions of the ground truth value. Okay. And again, if some of you have already looked at maybe some deep learning libraries or some literature about that, very often you are said, okay, this is the architecture of my model, and you should find good parameters to minimize the cross entropy, and the cross entropy is defined in this way. But maybe they don't explain why this is that. What I want to emphasize again is that this is just a consequence of first assuming a probabilistic model for y given x, and then following the principle of maximum likelihood estimation. And from this, then you have the cross entropy criterion which emerge. All right. So this is the thing we want to minimize with respect to W and B. So in deep learning, what we use very often are numerical optimizer, and we are usually using very simple, the simplest optimizer that exists, which consists in using gradient descent on the parameters of the model. Okay, so let's say that L, which corresponds to this whole thing, this whole sum, okay, depends on some parameter theta. So in our case, theta for the logistic regression model would be the W vector and the B scalar, okay. But as we'll see, we could have more parameters than these two things. So generically, I will say that the parameters of my model from now on are theta, and I will try to minimize this loss function. Okay. So in gradient descent, what we'll do is that we'll simply use local linear information to iteratively move towards a local minimum. Okay. So basically what we'll say is that if the loss function that we want to minimize is this black curve there, okay. Of course, I don't know. I could not plot that I could not plot it for any real problems, but this is a toy problem. But let's say this is the thing I want to minimize. Okay. What we do in gradient descent is that, okay, let's say that my current parameterization, so the current values of my parameters correspond to this blue dot. Okay. What I want is to make an update of this parameter such that after the update, the value of my loss function would be lower than before, smaller than before. Okay. So what we do in gradient descent is that we basically just assume a first order Taylor approximation around the current parameterization theta 0. Okay. So if you remember, a first order Taylor approximation is a function. So every time I put a theta symbol, at symbol, it means that I'm considering an approximation of the quantity. So what I'm saying is that an approximation of that loss is a function which depends on the current parameterization theta 0. Okay, and this function will have as argument some epsilon, so some step that I can take in the neighborhood of this theta 0, and I will say that, okay, if epsilon is equal to 0, then my approximation is equal to the loss function itself at theta 0. And then as soon as I depart from theta 0, so when as soon as I depart from theta 0, so when epsilon is strictly positive, then I will say that, okay, I'm like assuming a linear approximation in this neighborhood. Okay, so this is given by the gradient of the loss at theta 0 with respect to the parameters theta. Okay, and I take the dot product of this gradient with respect to the step epsilon that I'm taking around this theta 0 point. Okay, and on the other end, if I go too far away from this theta 0, then I'm basically saying then I have some quadratic penalty which I define as 1/2 times gamma of the norm of the step epsilon that I'm taking, the square norm of the step that I'm taking. Okay, so this is what I assume. This is the local approximation that I assume when I do gradient descent. And now, well, again, I want to minimize this approximation. I know that I will not be able to minimize the function itself directly, but I can minimize my approximation. Okay, and the way I could minimize it is, again, I would take the gradient of my approximation now with respect to the step epsilon. I would say this is equal to 0, and then I would solve for epsilon. Okay, and now if you solve for epsilon, then the step that you should take, the step epsilon that you should take, is given by 1 minus gamma over times the gradient of the loss at theta 0. Okay, if you solve for this, so you would have this that pass on the other side of the equation, the gamma which would be appear up, and then you would have epsilon equal to minus gamma times the gradient of the loss with respect to the parameters. Okay, and that just means, okay, if I assume this parabola in red, then you know exactly how to minimize, to find the minimum of a parabola. Okay, and this minimum is given by the step epsilon that you should take from theta 0. Okay, so that means now you will move basically from the blue dot to the green dot, and the step that you should take to arrive there is given by minus gamma times the gradient of the loss. Okay? So formally, what the update rule that we'll use in gradient descent is to say that, okay, I will start from some parameterization theta t, initially theta 0, and then I will make a step in the opposite direction of the gradient times some gamma parameter, okay, to arrive to a new parameterization theta t plus 1. Okay, and then I will just keep iterating like this by applying this rule over and over until I arrive to a theta value which has converged. It may not correspond to the global minimum. You may just arrive to a local minimum, or you could arrive to a plateau, but that's fine. Okay, and I don't want to explain why it is fine in deep learning. I invite you to follow my next course if you're interested, but this is typically what we do. All right, so let's see how it would work, starting from the blue dot and then applying gradient descent over and over. So we would start from the blue, would compute the orange, and then would use this orange dot as the new parameterization. In this new position, we would recompute this approximate model, compute its minimum. That would give us the step that we should take and to arrive to the new orange dot, and we'll keep iterating like this until we arrive to a point where we are not making any improvement anymore. Okay, so I'm simplifying a bit here, but this is really, in essence, what we do to optimize logistic regression models, and what also we use to optimize neural networks in deep learning. Okay, so far what we've done is that we've defined the logistic regression model, which I also call the logistic unit, which is some function which compute the dot product of W and X, and then pass it through a non-linear activation, in this case the sigmoid activation, the sigmoid function, to produce a new scalar value H. Okay, this is the model that we've considered so far, and we've seen how to optimize the parameters W and B of this model using gradient descent. Okay, now these simple models can be actually composed together in parallel to form what is known a layer with Q different outputs. So what we'll do is that we'll consider simultaneously not one, but several of these units, okay, with different parameterization of W and B. And so together, they will not longer produce a single output, but will produce as many outputs as you have units, okay? And so this composition of units, we'll call that a layer, okay, with Q different outputs. And we'll define this layer. Now we'll upgrade basically the vectors W and the scalar B into a matrix W and into a vector B. Okay, and so now if you take the matrix vector product of W and X, if W is of size D times Q and X is of size D, then you produce a vector of size Q. B would be a vector of size Q, so the sum would be a vector of size Q, and then you upgrade also the sigmoid activation so that it corresponds to the element-wise sigmoid activation. So you just apply the sigmoid activation on each one of the component of the resulting vector, and that produces the H vector, okay, of size Q. Okay, so I missed a question in the chat, which is about gradient descent, and it says, okay, if we had changed the initial condition, so the initial value from which we start the optimization algorithm, then could that lead to another minimum? And the answer is yes. Of course, for example, if you had started at this position where I have my mouse, then if you were to apply gradient descent from this parameterization, you would have found this other solution. In deep learning, this is usually not an issue because we would not be dealing with a parameter space of two parameters, one parameter as shown in this plot, but with a parameter space which is millions or hundreds of millions dimensional. And so it's very unlikely to have this kind of, how do you say, some kind of, in French you would say cuvette, where you are stuck in a local minima. Okay, so we've just defined a layer, okay, as a parallel composition of logistic units. Now, well, if you remember your circuit classes, you can of course compose elements in parallel, but you can also compose them in series. And so if you do that, now if you compose layer in series, so where you say that you start with some input H0, which is initially equal to the data, and then you pass it through a first layer, what you would obtain is a new vector H1. And then if you say that this H1 now is the input of a second layer, okay, then you would obtain a second vector H2 and so on and so on. You could repeat that L times. Okay, so you could chain L different layers to so that at the end you obtain a vector representation HL defined as this sequence of nonlinear activations. Okay. And so if you do that, what you obtain at the end is a model known as the multi-layer perceptron, or also known as the fully connected feed-forward neural network. Okay. And this is a very powerful model actually, which you can use both to do to solve regression problem and classification problem. So if you want to do regression problem, you would basically just keep the very last activation function. But if you want to do classification, let's say binary classification, you could just use this this very expression that I have in the slide. But you should just make it such that the very last layer just has a width of 1, so there is only one logistic unit. So that, of course, you would have to adjust the dimensions of W and B, but you would do that. And then at the end, that would produce then a single scalar value that you can interpret as P, as the conditional probability of the positive class given the input X. Okay. So another way to see that, if you then expand all these expressions and maybe plot them in diagram, this is very often the kind of drawings that we see in deep learning in neural networks, is that, but this is just representing exactly the same information as I've told you. We would start with some inputs that are shown with these circles and that represent the components of our X vectors. And then these components are just aggregated together through the logistic units. So first you have a dot product between this vector and all the and the W vector represented by all the arrows pointing towards this node. Okay, that would then so the result of this sum would correspond to the dot product of W and X for this specific W, and then you would pass this dot product into a nonlinear activation function. So the one we have seen is the sigmoid activation function, but actually there are other choices. Another popular one is the ReLU activation function, as shown by this symbol. And then you would do that for different values of W for as many logistic units as you have. So in this case you will have 3. So you would pass from a vector of size 6 to a vector of size 3. Okay, and then you would repeat the same architecture in the next layer. In the next layer, let's say you would have 2 logistic units, and so each of them would compute some dot product between these now 3 element vectors and this W first, and this other W for this second unit. You would pass this these dot products into a nonlinear functions again, and that would produce the output of the next layer. Okay? Then you would repeat that for a few times for L different layers, and at the end, you would produce the final output of the neural network. Okay. So the question maybe, so how then, so if this is your expression, how do you optimize how do you find the parameters theta of this neural network? Well, it's exactly the same as for the logistic regression. What you would do is to perform gradient descent on this expression, except that now this sigma of the dot product of W and X would be replaced by the computation of the neural network. But otherwise, the objective function would remain the same, and you would minimize it in the same way using gradient descent. Except that now the parameters would no longer be only those of one unit, but would be those of all the units that compose the neural network. So of this unit, of this unit, of this unit, of this unit, and this unit. All right, so let's move on now. So in deep learning, so most of the current success of deep learning is often attributed to convolutional neural networks. And so you can see convolutional neural networks as an extension of the fully connected architecture that I've just shown you, the multi-layer perceptron, in which we have layers, two new types of layers. First layer that we call convolutional layer, which will basically just implement the same kind of computation as in a regular layer, but the difference will be that each unit will not look at the entire input vector, but only at a small region of the input vector, okay? And then each unit will share the same weight vectors, okay? So effectively, that will result in a layer which will compute the cross correlation of the input through some learnable kernels or filters. And the kernel of the filters would correspond to this W vector that you would have in a regular feed-forward or fully connected layer. So this is what we call a convolutional layer. And basically it's a way to take an image as input and then to compute a new representation of that image in which you're basically detecting some patterns that correspond to the kernels, to the weights that are currently set in the neural networks, except that these weights, of course, will be learned. Okay, so if you go back to this analogy or this explanation that I gave you with the neural networks that would try to detect cats and dogs from pictures, I told you that manually what you would do is to try to maybe build some kind of edge detector, and then from these edges to build shapes, and then from these shapes to compose them into body parts. This is basically what these convolution layers are doing. They are the feature detectors that you would use, for example, to detect the ears or the edges, except that the feature detectors would not be hard-coded by yourself, they would be learned from the data. And then the second kind of layer that you have are pooling layers, which are basically taking as input a volume of features, for example, the output of some convolutional layer, and then to reduce the dimension of this input, of this volume, into a smaller volume, but in which the spatial organization and the structure of the data is preserved. Okay? It's basically, so you can do basically pooling as some kind of downsizing operation where you compress this volume into this smaller volume. Okay? And then what would happen in a convolutional layer is that you would compose these convolutional pooling layers in chain. So we would have, for example, a first convolutional layer, then a pooling, and then a second convolution layer applied to the result of the pooling layers. And effectively, that would mean that now these convolutions are looking at, since the pooling has decreased the size of the feature volume, would be looking with respect to the original image at larger parts in the image. Okay, so this is because we are combining convolution and pooling that the next convolutions in this layer, for example, are now trying to combine, to compose the features, the patterns that you've detected in this layer into larger, more abstract patterns. So like composing ears and eyes into a more abstract pattern, which is about the head of the cat. Okay, except that again, this composition is learned from the data. And then finally, you do that a few times until you arrive to a very abstract representation. Once you are there, you just flatten this volume into a flat vector, and then you feed that to a regular multilayer perceptron, in which eventually produce or predict a class for the input image. Okay. What you should notice also is that if this last layer, this one or this one here, so this last layer is a sigmoid activation of some linear combinations of the previous layer output with this W vector. Okay? But this very last layer is actually nothing else than a linear regression model, but now no longer apply to the original representation of the data, but apply to this final representation of the data learned by the neural network. Okay, and so this is why, and this comes back to your question, this is how neural networks manage to combine this very simple model into more complex one, because what they will do is that they will try to learn a representation of the data such that in this new representation, it becomes very easy to distinguish, to separate data from two different classes. Okay. So the data from two different classes, you will try, the network will try to project those points in an hyperplane in which there is no overlap between them. All right, so if you look, for example, at the prediction of such a convolutional neural network, this is what you would have. So let me pause maybe. So let's say this is the input of the convolutional neural network. Then what would happen is that you would have a sequence, a series of different layers. This very first layer would be a first convolutional layer, as I described. Then the second column would correspond to the nonlinear activation. So if you pass the output of the convolutional layer, for example, to sigmoid activation, then you would have this output. And then you could, for example, and this is what is done in this network, to feed that as input to a next convolutional layer, again, pass that through a nonlinear function like the sigmoid function. And then in the fifth, you could pass this output, this resulting output, into a pooling layer to reduce the effective dimensions of the data. And then you could repeat this architecture, convolution, sigmoid, convolution, sigmoid, pooling 3 times. So you would have 5 more columns and then 5 more columns. And what you see is that the deeper you go into the network, so the further you go on the right, correspond to the deeper layers in the network, the more abstract, the more scrambled the features become. Okay, so you can distinguish less and less the bird which was in this image. So that means basically the network is learning an abstract representation of these images, in which now it becomes more easy to fit a linear model to predict the class. Okay, and finally, you would have the prediction in this case with these 5 different classes. Okay. So this algorithm is not something that new actually. So convolutional neural networks have been proposed in the 80s. by several researchers, including Yann Lequin, but also Geoffrey Hinton, Yoshua Bengio, and others. And so this is a video from 1993 in which they show the results of a convolutional neural networks applied to these images, where we try to recognize digits and we try to basically read the digits that are shown. So this is it would not be that easy to program in a regular program directly, because as for images of cats and dogs, you may have a huge variations in how you can write the same digit, like this, for example, or like that. So this is Yann Lequin. I showed you a video of him at in the very first lecture. This is when, of course, he was younger. But the network he was using is exactly this one that you have in the slide. Okay, so now moving on. The last thing I want to show you today in terms of deep learning is recurrent networks. So you can actually adapt the multi-layer perceptron architecture or the convolutional neural network architecture to be able to process not only flat vectors, but sequences of vectors. Okay, so when the input now is a sequence of T vectors, okay, then the feed-forward network can be made recurrent by now computing a sequence that I will denote by H from 1 to T of hidden states, where Ht is a function of both xt and the previous hidden states. Okay, and this function of both xt and the previous hidden state would be, for example, implemented as a multi-layer perceptron itself. Okay, but it could be something simpler, but it could be that. And so, for example, the hidden state T could be computed as the sigmoid activation of some matrix vector multiplication between some W that I would have to learn and the input X, right? Plus some other matrix vector multiplication of some other W matrix with the previous state Ht minus 1, plus again some offset if we want to have an offset. Okay. So now that means the neural network would take the input one by one, the input vector one by one. Yeah, sorry, actually there is it should not be X there, it should be Xt, because of course we are processing this vector. So the purpose of that is that now with this architecture we'll be able to process a sequence and to remember what we have seen in the past. Okay, because now we have the freedom, we are using this Ht, which is, you can view as some kind of memory, which encodes what we've seen before. Okay, and this function, which in this case is quite simple but could be more complicated, is basically saying how we should make an update to our internal state, to our hidden state. Okay. And so this is actually very similar to what we have seen last 2 weeks ago, when we talked about filtering or dynamic decision networks. Okay. Because you can view this hidden state of a recurrent network as some kind of current value states. Okay, which in our case we called P of xt given some sequence of evidence. The sequence that we ingest with a recurrent network, so the sequence of vector from 1 to T, would correspond in this case to our sequence of observations, what we called the ET, the observations, the evidence ET. And what we do in recurrent network is that we compute some vector some hidden state ht+1 from the current belief state ht and the latest evidence xt. Okay, and we do that through some fixed but learnable computation. Okay, we do that, we make the update through this equation. Okay, but the difference is that even though this computation is fixed, it's a parametric computation in the sense that we can make it, we can learn the parameters w and the matrices w and this vector b. And this function can be arbitrarily complicated if you replace it, for example, with another neural network like a multi-layer perceptron. Okay. And so this is similar to what we did when we implemented filtering. What I told you is that we would have, we derived a fixed computation in which, if you remember, what we did is that we started with the current belief, we projected it through the transition model that we assumed, and then we obtained a predicted beliefs at the next time step, but then we made an update to these predicted beliefs given the evidence. But this whole thing together, which we said it could correspond to a single function that we call the forward function. Okay. What I'm now saying is that you can view the recurrent network and this update as also a forward update to your hidden state, except that now this is not motivated by some transition model and some explicit relationship that you know between the hidden state and the evidence, but by a model which is a recurrent neural network and which will just try to maximize some objective function that you define by adjusting the parameters of its internal computation. Okay. Then what is nice then is that HT, this hidden state for the recurrent network, of course, can also be used to decide on some action. For example, if you feed as input this internal state through some other learnable neural network F, which would then have to predict some next action to perform at that next time step t. Okay. So this is basically to show you that there are connections and analogy between what we've seen in the case of explicit probabilistic graphical models like filtering and neural networks like recurrent neural networks. And so this is actually quite powerful. So in this video, I will show you how this guy actually used recurrent neural network and how he trained them to play the game of Mario Kart, in which what you have as input are a sequence of images like this one. They are simplified images that you collect from the game screen. And then he will record himself playing the game. And then we'll try to use a recurrent neural network to determine what is the next action he should perform to imitate how he would play himself. Okay, so let's see how that would work.
Welcome back, Seth Bling here. 3 of these carts are being driven by a recurrent neural network I call MariFlow, so called because I wrote it using the TensorFlow machine learning library. One of them is being driven by my dad. Just kidding, this is him. See if you can figure out which cart he's driving. A neural network is a type of artificial intelligence which can learn by example. In this case, I've trained the neural network to try and mimic my own playstyle. MariFlow carefully examined 15 hours of my own recorded gameplay in order to try and figure out exactly how I tend to go about using the controller to drive the cart, so that it can drive just like me. The network started out knowing absolutely nothing about Super Mario Kart, and its only source of knowledge about the game was that gameplay footage. The goal is for its driving to be indistinguishable from a human. If you haven't figured out which screen is my dad yet, this is your chance to pause the video and rewind. Okay, this was the one that was being driven by my dad. He's still learning. I've let MariFlow do quite a bit of driving on its own. It's been able to get gold medals in 50cc mushroom and flower cups, though it's only ever managed to get a silver and a star cup. If you want to see MariFlow driving those entire cups and winning those medals, I've included links in the video description. Those videos will also give you a much better overview of how MariFlow tends to drive in all kinds of situations. You may have seen another neural network project of mine in the past, Mario. In that case, the neural network evolved on its own via genetic evolution to become better and better at playing the game. It produced small networks with evolved connections. The network in this video, MariFlow, is different. It doesn't know or care how well it's playing the game. Its only function is to mimic my gameplay style as close as possible. It can't learn that from its own gameplay. It can only learn from my recorded gameplay footage. Also, MariFlow's network always stays the same size. In this video, the networks have 2 fully connected layers, each with 200 long short-term memory cells, LSTM for short. In a regular neural network, called a feed-forward neural network, data flows from one layer to the next. We start with the inputs, in this case a low-resolution grayscale version of the screen. Each pixel is represented by a number between -1 and 1, and there are a few extra pieces of data as well. Then we apply a large set of simple computations, mostly multiplication and addition, but also the occasional application of a nonlinear sigmoid function. The computation factors in both the values of the inputs and also a set of weights which belong to the neural network itself. This gives us a set of 200 numbers between -1 and 1, which form the first set of neural activations in the first layer of the neural network, again represented here by grayscale pixels. Similar computations propagate neural activity one layer at a time. The deeper layers are able to represent more and more abstract information about the inputs. Finally, the network outputs 8 values, one for each button it's capable of pressing. These are the network's predictions of what buttons it thinks I'm likely to press and how likely I am to press each one. All those computations happen 15 times per second, as the neural network constantly updates its controller predictions. However, MariFlow is not a normal feed-forward neural network. It's a recurrent neural network. This means that from one time step to the next, each neuron may remember some information that it had in the previous time step. This makes each neuron act like a memory cell in addition to performing computations. In order to train the neural network, we need to adjust the weights that guide the computation during the forward pass, and let it learn what information it should try to remember. So, I recorded 15 hours of training data. I drove the cart around, recording both the neural network inputs and my button presses in each time step. In each time step, we run the neural network forward to get its predictions for which buttons it thinks I'm going to press. If it gets it right, we don't adjust the network. However, if it gets the button presses wrong, we use some calculus to apply small changes to the weights of the network so that in the future, it'll get closer to the right answer in a process called backpropagation. We also propagate changes backward through the time steps so that the network can learn which information to remember in its memory cells and which information it should just forget. By doing this over and over on all 15 hours of training data, the network slowly starts to get better and better at predicting my button presses. However, I realized pretty quickly that if MariFlow was just trained off my own gameplay footage, there was a problem. It could drive okay for a little bit, but it would inevitably encounter situations that were not like anything it had seen in the training data. It would start to produce more and more erroneous predictions and get itself into situations it had no hope of escaping. My solution was to record training data in interactive sessions. I would let MariFlow's predictions drive the cart for a bit, then I would take control for a bit, and pass it back and forth. This allowed me to get good samples of the types of errors MariFlow was likely to make when driving on its own, and then record training data that would let the network learn how to rectify the situation. This gave much better results when MariFlow started driving on its own. This project taught me a lot about how to create and train neural networks. I've been impressed that MariFlow is capable of winning races, despite the fact that it doesn't know what winning a race even means. I also think that if it had more training data, it could still get a lot better at the game. I'm releasing all of the source code and all my training data, so if you want to try and train a better neural network, there's a download link in the video description, along with links to more footage of MariFlow in action. That's about it. Thanks for watching.
Right, so this is, I think, a nice example of a recurrent neural network. What you may have understood from this is that this neural network, at least in this video, it's only good at imitating what someone else is doing, but it's not, so that means it will not be able to, for example, become better than that other person. And that would be true, it would just try to replicate. But this same kind of architecture will be able to reuse them when we talk about reinforcement learnings, 2 lessons from now, in which we'll no longer have to try to imitate someone else playing. It's the agent himself which would interact with the world, the environment, and then would discover by itself the consequences of their actions, and then would use that as a reward and then we try to maximize it. And then we would have, in this kind of setups, then really fully autonomous kind of self-learning and self-improving agents. But still, I think this video was nice to tell you about recurrent neural networks, how you train them, how you architecture them, and how simply by just trying to reproduce someone else playing, you can already achieve very satisfactory results. Anyhow, moving on, the last thing I would like to mention is that deep learning is not only about defining a multi-layer perceptron or a recurrent neural network. You should really view that now as some kind of high-level architectural language. And so this is, for example, a quote from Yann Lequin that you saw in one of the previous videos. And he says that now people are now building a new kind of software by assembling networks of parameterized functional blocks, and then by training them from examples using some form of gradient-based optimization. And by that, with this quote, what I want to insist on is that you should view deep learning really as a change of paradigm in how you write programs. So it's no longer about writing nicely packaged modular applications in which you have methods, function, classes, each of them implemented with primitives like if statement, loops, and so on. All of these things, up to a point, can be in a way replaced by some kind of composition of neural networks. And then instead of explicitly saying in the program what you should do at every step, at every operation, you learn what you should do from data. And so this is really a shift that is happening now across many fields, across fields of engineering, sciences, and many others. And more now, these neural networks are becoming this kind of not fixed but learnable architecture, but some kind of learnable programs by themselves. Okay. And so, for example, this is the toolbox that now exists in deep learning, even though this is actually quite, this is a few years old already, but you can apply deep learning, of course, you have feed-forward models as the one that we have seen, but you can also process sequences, so you can ingest sequences and predict sequences using recurrent neural network architectures. You can operate on hierarchies. You can implement key value stores. You can run neural networks on top of graphs. You can have attention mechanisms and many other things. There are now even some kind of differentiable computer architectures in which you try to learn how to make use of some memory in order to read and write from it, and then to by the program how to determine the control flow that you should apply, and so on and so on. So this is very rich, and what I want to say is that it really goes beyond the mere and the simple feed-forward fully connected neural networks. Now deep learning goes way further than this. Okay. And finally, I also want to take the opportunity of this lecture about machine learning and deep learning to say a few words and to take some perspective. So everything that we have seen and that we are seeing in this course is motivated by example that I'm using the game of Pac-Man as a driving example, but of course artificial intelligence is much more than just playing games and playing Pac-Man. Pac-Man is just a pretext that I use to introduce the algorithms. What I want to say also is that the applications of AI, and more specifically the applications of deep learning, goes much beyond that. And so I will just show you 3 videos that all of them make use of deep learning to implement things that are very non-trivial in order to solve very concrete engineering problems, very important problems. So in the first video that I will show you, it's about how you can use neural networks in a self-driving car in order to make sense of the environment around the car itself. And so what you would have as input now is a sequence of video frames, and what you would like to predict is, for example, to produce segmentation maps in which you say that this pixel, for example, corresponds to a person, this pixel corresponds to the road, these blue pixels correspond to other cars that are moving, and so on and so on. So I will show you this one. I will also show you how you can use deep learning, for example, to solve problems in agriculture, for example, so this is again an example of convolutional neural networks in which you can use, for example, to detect disease that you would have on plants. And finally, the third one is how deep learning is used, for example, in healthcare, in medicine, to improve the diagnosis of, in this case, tuberculosis. So let's look at the first one.
In autonomous vehicle software, deep neural networks are often trained to detect an object using a bounding box around the object. Today in Drive Labs, we're going to talk about using a DNN to provide pixel-level accurate object shape information. This is known as panoptic segmentation. In the top video, we see pixel-level shape segmentation results for different object classes, with vehicles in blue, pedestrians in red, and drivable space in green. And in the bottom video, we see segmentation of these object classes into individual instances, as shown by their unique object IDs. So each of the pedestrians at this intersection is detected and tracked as a different instance. We detect object shape details, including the rearview mirror on the bus coming towards us, unusually shaped trucks, and the precise shape of a trailer. And despite occlusion by the tree, this car is still detected as a single instance. And here we see accurate segmentation of drivable space around traffic cones and on-road traffic signs. In this clip, the panoptic segmentation DNN is segmenting both cars in drivable space accurately in an unstructured environment. Panoptic segmentation of objects in free space provides a deeper and richer understanding of complex scenes, such as dense traffic with vehicles occluding each other, or construction zones with unusual object shapes, or corner cases, such as pedestrians carrying large objects.
So this is some research done at NVIDIA, which is it's a research lab doing deep learning, but mainly also producing GPUs, so the kind of computing device that you need to train now these modern neural networks. If you're interested by more applications of neural networks on self-driving cars, I really invite you to check on YouTube. If you click on this link, there is a channel from NVIDIA Drive Labs with 10 or 20 episodes, I don't know, in which they tell you about basically all the components that they have implemented, most of them being based on neural networks to implement their self-driving car. Next, this video.
Cassava is a really important crop. It provides for over 500 million Africans every day.
When all other crops fail, farmers know that they could rely on their cassava plants to provide them food.
There are several diseases that affect cassava, and these diseases make the roots unedible. It is very crucial to actually control and manage these diseases.
So we're trying to use machine learning to respond to those diseases.
And TensorFlow is the best foundation for our solutions. The app that we've designed can diagnose multiple diseases. It's called Nuru, Swahili for light, the light that farmers can use to see their problems and find solutions. You wave your phone over a specific leaf, look at it, and if it has a symptom, a box will pop up saying you have this problem. When you get a diagnosis, we have an option for you to get advice and learn about the best management practices.
The object detection that we use through TensorFlow relies upon our team annotating images.
We've collected over 5,000 high-quality images of different cassava diseases for this project. We use a single-shot detector model on a mobile net architecture. It's able to make predictions in less than 1 second.
Instead of having to implement thousands of lines of code, TensorFlow provides a library of functions that allow us to build architectures in much less time.
We need something that can be deployed on a phone without any connection. TensorFlow is able to shrink these neural networks to be able to fit on your mobile device.
The human input is absolutely critical. We're really building something that augments your experience and makes you better at your job.
So with AI tools and machine learning, you can improve the yields, you can protect your crops, and you can have a much more reliable source of food.
AI offers the prospect to fundamentally transform the life of hundreds of millions of farms around the world.
You can see a product that can actually make someone's life better. This is kind of revolutionary.
Right, so this was for the second example. I picked this one because I think this is a very concrete and important problem, which is rooted in real life. And so this is, I think, a nice example of what you can do with machine learning as engineers or computer scientists. Also, they mentioned this library TensorFlow. So TensorFlow, you should just know it's a Python library to do deep learning. It's one of the most popular ones. It's mainly developed by Google. If you have an Android phone, it's very likely that you have several neural networks running on it without you knowing, and most of them being running using some TensorFlow export format. So this is something now very standard and very popular. And finally, the last one, again by NVIDIA, about deep learning for tuberculosis monitoring, which is also an example that I picked because it shows you that as engineers, computer scientists, you can, with artificial intelligence and deep learning, contribute to many other scientific disciplines that are very important, that have huge challenges. And this is really some serious problem. It's not just playing Pac-Man for the sake of playing Pac-Man. Even though we've been using these examples to introduce the techniques, the same algorithms can be used to solve these more important problems.
The biggest problem in healthcare today is the increasing patient population, as well as the increasing range of treatment options available to the caregiver. AI is particularly good in this circumstance because it can reduce the burden by producing more pertinent information, better sifted data, and increases the range of available information to the caregiver. One of the biggest issues affecting low resource economies is tuberculosis. Despite being a treatable condition, it still kills 1.5 million people every year. High accuracy tuberculosis diagnostics already exist. However, for follow-up, it's more of a challenge. The way that this process works is that sputum is taken from the lung of each patient, it's stained, placed on a slide which highlights the bacteria. These are then counted by hand. The system we've developed uses a convolutional neural network to do the cell counting. It reduces the labour enormously and reduces the time per slide from 40 minutes down to 7, whilst remaining robust to all the vagaries of slide preparation, the low quality imaging from the microscope and the mobile phone camera.
ONTAP AI is a solution where NVIDIA and NVIDIA's partners bring together an AI solution that is rapidly deployable, that brings both storage and compute together to enable artificial intelligence to be used in the healthcare setting. NVIDIA's DGX Pod is their flagship supercomputer system. This is especially important in the healthcare setting where we have large amounts of image data that needs to be trained, and this requires large amounts of GPU compute. This is all put together in NVIDIA's DGX Pod solution.
The advantage to Cambridge consultants of having the relationship with NVIDIA and with NetApp is that an on-premises AI platform allows us to develop custom algorithms for our clients for a wide range of challenging applications. This combination of expertise allows us to help transform our clients' businesses by delivering truly original, world's first innovation.
Alright, so that was it for the videos. So to conclude, I would say that, and to summarize what you've seen today, you should really view learning as some really key element of intelligence in general. In what we've seen, we've mostly focused on Bayesian learning and machine learning or statistical learning, which basically aims at learning probabilistic model, or rather the parameters of some fixed family of parametric models, and to learn these parameters automatically from data. So this is true for very simple models like Bayesian networks. This is what we started with in the case of Bayesian learning. But this is also true for more complicated models as you would find in machine learning. For example, linear regression model, linear classification model, and also it's the same principle that you would apply when it comes to learn neural networks. Again, you would follow, that's still the same recipe. You postulate some parametric model of some conditional or some probability distribution, and then you learn the parameter of this data following, for example, the maximum likelihood principle. Okay, and then it reduces very often to an optimization problem, which is rather simple because you have an analytical solution which is directly available to you, or and this is often what happens. You don't have access to such a solution, so you have to resort to numerical optimization. And in the case of deep learning, what we very often use is gradient descent. Okay. Then we mainly talked about today supervised learning, which is used to learn functions from a set of training examples, so for a set of input-output pairs. And then what we'd like to do is to find a mapping or probabilistic mapping between x and y, between input and outputs. We saw linear models, which are simple but usually good baseline for predictive models. But on many other more complicated cases, like if you are dealing with images, they are insufficiently expressive, and so then you would have to upgrade these models to more complicated models, like for example neural networks, which we define basically as a composition of squashed linear models, a composition of logistic units that you compose, for example, in series to form layers, and then in parallels to form layers, and then in series to form multi-layer perceptrons or convolutional layers, and so on and so on. So that's it for today. I hope you like this lecture. If this is a topic you find interesting, I really encourage you then to follow follow-up classes, follow-up courses that you will have access to in your master degree. In particular, Introduction to Machine Learning, given by Pierre Gerst and Louis Wenkel, and then the Deep Learning course given by myself. So if you take these two courses, then you will have a very good background and strong background when it comes to machine learning in general and deep learning in particular. So that's it for today.